Okay, this video introduces the mini lab called a simple pendulum. This video is specific to Conceptual Physics AB. Okay, so let's go ahead and take a look at this mini lab. You recall from lecture, first of all, that the period of oscillation of a simple pendulum is described by the following expression, where L is the length of the string. Notice that this expression allows you to measure g, acceleration due to gravity, without bothering to have to do a free fall experiment. For example, all that you have to do is take a pendulum of known length L, measure the period of oscillation, for example, at a stopwatch, and then the only unknown is g, acceleration due to gravity. So in this two-part mini-lab exercise, I lead you through a brief procedure on how to measure g. Okay, as I said, the procedure is in fact divided into two parts. So let's go ahead and take a look at part one. In part one, you're just discerning the relationship between the length L of the pendulum and the period capital T. We'll do so in the following way. This is a mini lab exercise that you can do at home. You're going to need a small object you can tie some string to. I'm using a washer. You're going to need some string. You're going to need a ruler or a meter stick, and you're also going to need a pair of scissors. So the first thing that you do is you construct a pendulum using a small object by tying the string to it, and construct a pendulum with a length of 1 meter. So for example, let's say that I might construct my pendulum, and I do so with a washer, and I have the string tied to it like so, and then L is going to be measured from where I pinch the string with my finger to, in my case, the geometrical center of my washer, which is its center of mass. So this distance right here is L. If you use a small object, measure L from where you pinch the string with your finger to the center of that object. Okay, now start with a distance L of 1 meter. And then what you do, using a stopwatch on your smartphone, is you time how long it takes for 5 oscillations. So for example, if I start with my pendulum like so, I start my clock when I say go, 1, 2, 3, 4, stop, like so, to measure the time necessary for 5 oscillations. Make sure that you measure the time necessary for 5 oscillations and not accidentally 4 or 6. If you're not paying close attention, it's actually easy to miscount. Okay, once you do, then start to fill out the following data table. This is the data table from part 1. Okay, it's going to have 3 columns. We're going to have the length L in terms of meters, and then 1.0 meter, 0.8, 0.6, 0.4, and 0.2. And then we have here the time, we're going to call it small t. This is the time necessary for 5 oscillations. So t is the time necessary for 5 oscillations. And then from there, the period, big T, can be found by taking that time and dividing by 5. So here in the last column in part 1's data table, that's where you then place the period. And then there's just a question or two for you to answer based upon your results of part 1. Once again, start with a pendulum of length of 1 meter, and then what you want to do is cut the string down like so, ultimately measuring the time small t for the following pendulums of these lengths. Okay, now in part 2 of the exercise, we're going to use this data, specifically the period and the length L, in order to actually measure g. Here's how we're going to go about doing so. Okay, as was described earlier, the period of the oscillation is described by the following expression. Okay, what we're going to do is just a little bit of algebraic manipulation to solve this expression for g. I want you to repeat this small derivation on the mini lab handout in the space provided. So in order to solve for small g, the first thing that we have to do is get rid of the radical sign. So let's go ahead and square both sides of the expression like so. And now I'm just going to cross multiply here to solve for g. Like so. So then therefore in part 2 of the exercise, we'll take our pendulums of length L, the period that we measured, and then we'll go ahead and plug everything into this little formula to calculate now g. So here's part 2's data table. Okay, we have the length L in terms of meters. Once again, 1.0, 0.8, 0.6, 0.4, and 0.2 meters. And then just write down the period, big T, for these pendulums of length L that you had already measured in part 1. So go ahead and just write those here once again. And then take these values of the length L and the period capital T, plug them into the expression to calculate G in terms of meters per second squared. Of course, in theory, you should end up with 9.8 meters per second squared. But due to various experimental errors involving timing the oscillations and perhaps miscounting the oscillations, what I want you to do in order to describe your results here is calculate an average. I provide for you space on the mini lab handouts to do so. So let me do some erasing here. And I'll have you calculate what we'll call G average. So just average these 5 values here, and then we'll make a comparison between G average and 9.8 meters per second squared by calculating a percent error. So your percent error is found by taking the absolute value of the difference between G average and G, 9.8 meters per second squared, take the absolute value of the difference, and then divide by G, divide by 9.8 meters per second squared. You'll end up with a decimal multiplied by 100 in order to convert to a percentage. And then just to finish the mini lab exercise, there's a couple of simple qualitative questions for you to answer at the end of the handouts.